Hello and welcome, everybody. My name is Masha Frodanovic, and I'm Program Director for SIAM Activity Group on Geosciences. And it is a great pleasure to have Professor Peszynska from Oregon State University here today. And before I let her speak, I'm just going to do a little bit of introduction just about SIAM and the upcoming conference, and then we will let Malgo take away. So one thing is that December 19th, so that is 10 days from now, is the deadline for our next conference on mathematical and computational issues in the geosciences. It's happening in Bergen in Norway, and I haven't been, but I'm looking forward to. And apparently the view from the conference venue is pretty much what you see on this slide. So views should be great, and so should be the scientific conversation, because this is the first post-pandemic in-person conference for SIAM Geosciences. So we are definitely looking forward to that. So get your abstracts ready, December 19th. March 20th is the deadline for travel award applications for a lot of people. Bergen might be a little bit outside of the budget constraints, so travel award and early career travel award applications should, any award money should definitely help. And then pre-registration deadline is approximately 1 month before the conference. So any questions, let us know. The way to keep up with anything going on in SIAM Geosciences is via SIAM Engage, and announcements go out, and it's not a lot of announcements, so it's definitely something that is easy to keep up with. And the Geosciences websites are updated as well. If you are a student and are interested in joining SIAM, there is a way to get free student memberships. So if you can't find the way to it online, please let us know. Now we have outgoing officers, so you can contact 4 people on this slide for another month until there is a switch. But we should be easy to find and are always happy to answer the questions regardless of officers being current or past. So Inga, Vladimir, myself, and Chris. And for the incoming 2 years, for the next 2 years, I will move to be a chair, which means that Professor Luca Formaggio will host these webinars in the starting spring. And then Chris here is vice chair, and we will have a new secretary, Irina Tesor. So we're looking forward to the new group. And again, any questions, do not hesitate to ask any of the officers. Now, without further ado, Professor Peszynska has had numerous awards that are really hard to line up. We will mention the SIAM award because that one is the most important one, right, Malgo? But she has also been, she calls SIAM Geosciences her scientific home, and is always, in my experience, available for any questions related to SIAM or in general, any scientific discussions. So we're very much looking forward to speaking with her today. And should you want to contact her about anything that is mentioned today, you can find her contact information from Oregon State University, where she has been a professor for a long time now. Now, if you want to ask questions during the Q&A, please raise your hand and ask a question, or just type it in. At the end, I will give you a chance to, I will unmute you and give you a chance to verbalize it yourself, or I can ask it for you. That's up to you. You can use chat for saying hi or any comments aside. And if you miss anything, this seminar will be recorded and posted on SIAM YouTube. And now, without further ado, we will let Ms. Malgo discuss how do we upscale from pore-scale to Darcy to field scale. And I'm looking forward to her telling me that, oh, my pore-scale can never be upscaled, or discuss anything relevant about the process. Malgo, I will stop sharing.
Well, thank you, Masha. So It's a it's a really intense pleasure to be speaking again for the SIAM audience. I hope to do it again in Bergen. Hopefully, all the situation outside our world here will, all the good things will line up so that we will all be there. So thanks for the introduction. And I want to say thank you, the outgoing officers. I have the pleasure to be probably the first one in a seminar to thank the outgoing officers and to greet the new officers. Both of them are here. So thanks for your service, and especially for this seminar webinar series. It's been really super informative, and I think it's really great. So thank you. All right, so Masha, I will not tell you that your pore-scale efforts are not great, the opposite, even though I might not have a lot of slides that specifically relate to the things you do, but I guess you will recognize some of them. So all right, so even though it's only my name on the title slide, I will acknowledge a lot of collaborators who have contributed to this work, and so you will see their names throughout the talk. And again, with an apology, I probably won't have the time to discuss everyone in the world's contributions to the multi-scale computational mathematics and geosciences. So I apologize in advance if your name or your papers are not cited. So let me start by acknowledgements. So I had been working on this general, multi-scale applications in geosciences for quite some time. Somewhat unexpectedly, I was handed this as a project for my PhD thesis by my PhD advisor. And you see here a picture from sort of a fissured, fractured media from my PhD thesis. My goodness, I didn't even have any PDF of that anymore. And then most recently, I have, well, not super recently, but I have had a lot of work done with a colleague who passed away in 2019. So I would like to feature her name here as, the main thing. So thank you, Anna Trykowska, and thank you all of the other collaborators, including our late Jim Douglas, Mary Wheeler, Ivan Yotov, a lot of the students, Christiana Garibaldi, Vivi Klein, Dorthe Wildenschild, and Masha. We tried to do something called a pore-scale benchmark, and we succeeded for a while, but then Masha took over an amazing and created this amazing digital rocks portal, which I think is doing great. I was just checking 2 days ago, and it's a great resource. Thank you, Masha. And then with other students, most recently, we have worked on some practical, pore-scale to Darcy issues, which kind of gave us a pause. And this is why I have a keyword seriously at the end of my title. All right, so you will see the names of those students popping up and collaborators. Last but not least, a lot of the work that I've done from core to field, especially the theoretical work, was done with Ralph Showalter, who is today online. So thanks, Ralph, for all of the inspiration. All right. So a few introductory slides, you will see that I will talk quite a bit about introduce some classical approaches and some classical information, because you will need this to be able to understand some of the things we've done, from pore to Darcy. And I will be making comments about how the pore to Darcy has been informed by the core to field or core to reservoir efforts that we've done before. So everybody knows, about multi-scale materials, especially about the composite materials made of, 2 or more materials. And a classical example is reinforced concrete. Now, everything here that I have is also porous media. So probably you all know that concrete is also porous medium, even though it's a particular porous medium. But in this picture here, it's important to note that it is a composite material made of 2 materials which conspire together to give you better properties than either one of these materials alone. Next, you have a picture of soil, rocks. This is what we live with in subsurface. We recognize their multi-scale structure and very heterogeneous one, which I will mention later. Next is a picture of coal. This is actually picture of coal cleats and in other words, fractures, along with blocks of coal, which provide a hierarchy of multiple scales. I won't focus on this today, but we've done some work with Darcy on it. We also see a picture of mangrove forest, which Clint Dawson and his collaborators used as an example of, porous media, and flow through these can be modeled using, for example, some non-Darcy models, and you can use some of them to upscale from pore-scale. You also can have skin, definitely a porous material, but maybe not in subsurface most of the time. And then here is a picture of cross-laminated timber that was used to construct, produced actually at OSU, and was used to construct some, buildings here. All right, the far motivation for this talk has come from our work on upscaling from pore-scale to Darcy scale, and hopefully being able eventually to go to the landscape scale in the permafrost zones. So I will touch upon this at the end because these approaches included or require that we use additional physics, but I will build up to it as we go. All right, so here we go. The traditional view of multiple scales in modeling and progress has been made traditionally in this green zone here. So people started working with Darcy scale data, and in order to combat the tyranny of complexity of computational models at the reservoir scales, very frequently people had to upscale. In particular, the work that was started on fractures originated here. However, with the availability of imaging, in particular of pore-scale, and Masha and Dorthe Wildenschuld played a very substantial role in these efforts. People started looking at being able to work also at the pore-scale. So to a certain degree, the work, below these scales, the atomistic, nanoscale, up to maybe the micrometer scale, the pore-scale, probably should be or could be described by some kind of discrete models. And by this, I mean frequently people use lattice Boltzmann or approaches like that. Well, these days, however, we feel like we should be able to simulate things at pore-scale using continuum models. So here you have another view of this multi-scale hierarchy, where you hope to start at the pore-scale, then upscale to the lab scale or Darcy scale, and then move on to the reservoir scale. Of course, the difficult thing is to maintain connections between the scales as the coefficients or regions change dynamically. So you should be also downscaling. And that's probably one of the hardest things to maintain. And we have seen efforts in material science where people go from, atomistic scale and understand the physics really at that level, or maybe a little higher than the atomistic scale, and upscale to the lab scale. I'll mention this at the end in the context of physics. Now, the picture on the right-hand side is suggesting to you that most of the time, the early efforts especially, we're focusing on, idealizing what the geometry at the pore-scale is, recognizing that especially the mathematical results, rigorous convergence and whatnot, requires, some assumptions. You have to start somewhere. So very frequently we would start with sort of synthetic porous media, and so viewed here as a collection of grains, and you have here the flow solutions in between them. And then you would try to upscale to the Darcy scale. But as I mentioned here, this carries with itself a really big burden of, 5, potentially 6 length scales, difference of magnitude between the length scale. So this is incredibly complex. And, if you want to image a sample of, 1 centimeter size, and then you get out of that, let's say 10 million voxels to solve your flow problem on, this becomes frequently untreatable. You can do it once, you can do it 10 times, maybe you can do it 100 times, but at the end of the day, you probably won't be able to do things like that in real time. So one possibility is to introduce an additional scale, and Masha and others have worked on the pore network scale. We picked this up in an effort to try to understand how things would work when the pore scale geometry is changing. So the pore network scale will be the intermediate one. All right, so now we go to the classical approaches and some definitions, and some of them will be quite mathematical, which is, of course, perfect for this audience, but we'll eventually land with a lot of pictures and simulation results. All right, so first, homogenization. Typical approaches and the work that I mentioned earlier that started on fractured media assume that you have some sort of a periodic geometry with coefficients that vary largely. So for example, here you have those slow flow regions in blue separated by, let's say, fractures in red that are highly permeable. And so the assumptions about that kind of geometry and about that kind of composite medium allow the classical homogenization approaches. And I listed here sort of the steps that when people learn this material, they frequently start with, learning how to do asymptotic expansions, how you would, out of these asymptotic expansions and some kind of a closure on the, PDE, would develop effective models. There's also a question of scaling, what kind of order of epsilon you would use to scale your viscosity or your permeability or whatnot. You would also want to know that the problems you're posing are well posed, so that is possible to do. And you would want to then understand how the asymptotic analysis you're carrying out, how well they approximate the original solution. So I'll make that point later, but let me tell you, in a real porous medium, we work with a fixed scale epsilon. So maybe epsilon 0 is the one that we have the data for. Yet, of course, the asymptotic analysis or whatever delivers effective solutions that are limits as epsilon goes to 0. So you never get quite the same solution as the one at the fixed epsilon scale. But what you get out of this is you get an approximation. All right. Then once you have the mathematical results, you can look at them in many different ways. One of them is to set things up as a 2-scale problem, which we've heard the great talks already in the series. Last year was by Soren Pop, and thank you for that. You can also do upscaling, which is sort of, in a nutshell, I mean, I'm not going to be proposing this as a definition, but this is my sort of my understanding of it is, it's essentially a practical computational way to realize some of the homogenization ideas. It also frequently, upscaling is applied where the rigorous homogenization wouldn't apply. So, basically it's the pragmatic approach to just do it. All right. Okay, moving forward, let's look at some very simple examples just to establish vocabulary. Let's look at an elliptic partial differential equation. So this one is actually my examples here in 1D, so they are just differential equations. I'm looking at a problem with boundary conditions 1 on the left and 0 on the right hand side, and I'm looking at a problem where you have an oscillating coefficient K epsilon. So that's a classical setup. On the left hand side, you see maybe not a super smooth, but because this coefficient is plotted in green, does have some kind of a sort of singularity at the cell interfaces, but the solution corresponding to it, to the problem, the true solution in red is kind of smoothly varying, right? So the idea is that maybe you're not really interested in those small variations of that true solution, but you would like to see the effective solution. And the large scale trend here is, the linear, piecewise linear going from left to right. If you look at a problem now where your coefficient is piecewise constant, then you would obviously have the gradients of the solution have to adjust to that, the fact that the flux would be constant. And so therefore you have some, higher jumps in the gradient of the solution, but ultimately, actually, the global trend of the solution is the same. And so again, the idea is that you would like to be looking at some kind of upscaled limit, so effective behavior of the solution from left to right, and that's what homogenization delivers. Now, I'm not making precise in how we calculate that limit. This is a topic for a slightly different, more rigorous talk, that the one I aim for today. So in one dimension, you can derive actually what that solution U0 should satisfy. And this is a partial, differential equation with an effective coefficient, which everybody knows that in one dimension is exactly equal to the harmonic average of the coefficient. All right, so I'll move on now. And now let's look at a more general case of an elliptic PDE. We work in a very similar way. However, to get the effective coefficient, we have to work harder. Now you would have to solve some kind of a so-called cell problem, where you would be solving, I wrote the cell problem here. You would be finding the response of the solution, correcting eventually the decay to a unit impulse. So this unit impulse is the EJ, that's the unit vector in the J direction. And in the approach by Durlovsky, which I will quote in a minute, this whole portion is taken sort of to the right-hand side, or in other words, these two things together are put together in a kind of maybe a nicer way than the classical way that I displayed here. But it's a very useful way. So you do that and you solve your problem. And I have examples here picturing such a response in the direction X1, if you like, for a case with inclusions. So this portion is completely impermeable, and to the case without inclusions. All right, so then of course there is always a question, how meaningful mathematically are our solutions and our convergence results, and there's a lot of theory that people have developed for this over the years, and I won't be really dwelling on that today. Now, for other PDEs that are not, your elliptic linear elliptic problems in 1, 2, 3D dimensions, we always strive to find some kind of an effective behavior. So you want to find the solution U0 for which you hope to be able to find some kind of effective coefficients. But the question is it always possible? What happens if you have a problem that's transient? What happens when you have a problem that's nonlinear? And is the type of the operator that you started with always the same as the operator that you find in the end, so the effective operator? And the answer is generally no. In fact, from pore-scale to Darcy scale, you start with Stokes' model, for example, and you end up with just an elliptic PDE at the Darcy scale. Now, for nonlinear problems, the difficulty may be not tremendous, but computationally that's a big problem, is that now your cell problem is scale implicit. So what does that mean? This means that the coefficients at the pore scale now depend, even though it's a constant, but depend potentially on your solution. Might also depend on the gradient, but I didn't write this out. So what this means that if you wanted to solve a problem at the higher scale, you would have to a priori know your solution, U0, in order to be able to solve the cell problem. So you would have to do it by some kind of an iteration. Of course, there are ways to go around this, and we can find approximations of those kind of scale implicit approaches, and in many cases they're fairly easy. So this has been done. You can even find better models if the model, for example, transient model that you get by homogenization doesn't really work for you. You can find much better models. For example, the double porosity models are very well known for this. All right, and I'll give you some examples as we move forward on those approximations. All right, so for transient problems, and maybe not just for transient problems, the problem is that sometimes, depending on what problem you're working with, this average plotted here with the red line, a local average might not be really a useful approximation to what's really going on. And that's reflected by what kind of estimates you can get on the solution and its gradients. For large contrast between, in media, frequently you would have a situation where this red curve, for example, has really nothing to do with, it really is a poor approximation for what's going on. And that's would be reflected with the fact that you can only get estimates where the estimate on the gradient does blow up with epsilon. All right, so one way to get around this, and I'm mentioning this because the evolution problems that are the classical double porosity approaches actually gave us an understanding for the permafrost problem we're discussing today at the end. In a nutshell, you go from the elliptic problem now to a parabolic problem. You use some boundary and initial conditions, and what you see is a solution like this. All right, where sort of there's the solution in those blue regions where the diffusivity or I don't know permeability is very small, tend to stick to respond much more slowly to the boundary conditions imposed externally. So in the end, you have a solution that looks like this, and it takes a long time to work. So 1D profile of this, if you wish to look at the 1D profile of this, looks like this. So you have the true solution in blue, but then you see that it has sort of two envelopes, the red envelope and then the green envelope. So one responds to the slow time scale, the red one, and then the green one corresponds very well to the to the fast scale. So this, in a nutshell, is an idea of double porosity models, where you would, instead of looking on at one of the U0, the upscaled value, you would sort of work with a product, Cartesian product of knowledge, if you wish. I'm really sort of maintaining this in a very informal way, where you would maintain the information between these two variables. All right, and the work by Todd Arbogast and Jim Douglas was really fundamental in bringing the mathematics to a lot of the double porosity models that people have known over the ages. And this work does still inform us again, also for the permafrost model in a different way, but I'll talk about this in the end. So here is a slide with a lot of references on double porosity models. In particular, I want to mention some work that we've done, because that work also informs us on problems when you don't just have diffusion, like in the double porosity models, but you have strong advective effects. And with Song-Gyang Yi, we worked on upscaling such models and everybody knows that this additional variable that I mentioned, the slow variable, is represented in the global equation by some kind of memory terms, like the term here. When the scales are not separated, we found, in fact, that you would have to have a lot of additional terms, maybe two other terms that involve other spatial derivatives of the solution. So this was a great project, but anyway, I'll let you digest it. It's sort of is a dormant, but again, it informs what we do today. All right, so some current topics that I mentioned here, I will not dwell on these, but I will just mention that there is a lot of continues to be rigorous mathematical work, in particular on homogenization for nonlinear PDEs with non-smooth nonlinearities. And our work on permafrost was very strongly informed, in particular by the work by Augusto Vicente in 2007, who showed us how to upscale Stefan problem. And there's recent great work on upscaling coupled systems of PDEs, and I'll mention the references in particular to people from Bergen as we go throughout the talk. Now, I will also make points that there is a lot of physics that cannot be done by those traditional PDEs, and that's really what informed our work here. All right, so moving forward, we can go from core to field, and the major issue here is that probably most porous media, people would agree, are not really periodic. So you work with a permeability field that is just highly variable, and this is hardly a periodic medium, as you can see. But in order to combat the complexity of solving in detail with this kind of data, you would want to consider some kind of approximations, and you can do upscaling, rigorous upscaling, following the, in each cell you would compute some effective coefficient, or you could do some brute force averaging, taking arithmetic or harmonic averages, or even geometric, which I'm not picturing here, but which play a role in the permafrost project. All right, so again, many of these approaches have to grapple with the lack of periodicity, but that's okay. Now, as an example of battling the scale implicit situations, I have here an example of what we did for the non-Darcy problem. So again, the difficulty here is that your scale implicit problem would require that for every global variable U0, you would have to solve a local problem to get the coefficients that you would get and plug in again to the upper scale. So that's difficult to work with in general, especially with a lot of scales. But we've heard talks that show that people can do it. Our approach has been a little more pragmatic, perhaps, simplistic. So instead of looking at the scale implicit problem, what we do is one could just solve for the effective coefficient for a collection of inputs. So you would sort of, by almost, in a greedy algorithm, you would pre-solve even find your effective coefficient for a collection of inputs. And then when you do need a value of K effective at some U0, then you would just, let's say, interpolate between them or something like this. So what we did in this similar vein of with Cristiano Garibaldi is we apply this to the non-Darcy flow. And to be honest, this one had a very simplistic, very straightforward idea, because you can always try to start first by upscaling the Darcy problem and then subtract out what you're getting from upscaling and to get the so-called the beta, the inertia coefficient there. Now, I'm not going to dwell on this, but this work also informed what we did later for pore-scale. All right, I want to mention also other 3 elements of the core to reservoir upscaling that informed our work from pore-scale. In particular, I already mentioned the way that Ludorowski rewrote the cell problem. We found it much more easy to work with our simulations. So I encourage you to look again at that work and perhaps apply to your work. Also, I want to mention the work we did on mortar upscaling, which was later extended to, couple the pore network approaches. We applied that work also with students from here, from Oregon State, in later on. And then, of course, the major idea is to apply heterogeneous multi-scale method following what Masha present here and other people have done for the single phase flow model, and also I think they considered a two-phase flow problem. In the end, we were not able to take advantage of these approaches, but I'll talk about this later. All right, so now pore to Darcy. Moving forward, the major ideas is that went to the permafrost project is that we want to upscale coupled processes. So at the pore scale, you deal with some kind of a geometry, and I'm picturing here some images of the realistic geometry of sandstone. You see it's a very heterogeneous geometry at pore scale with a lot of small pores and with a lot of really large pores. We also can work with glass beads, which are somewhat easier to work with, plus they also offer a lot of advantages from the imaging point of view because glass beads are transparent, so you can see a lot of the fluids and image a lot of stuff more easily. So there, the difficulty is, in either way, the difficulty is handling a new phase that shows up. So here you have a picture of glass beads with on the right hand side and without the biofilm that was imaged in Darcy Wildenschultz group. So we work now with models that we defined at every representative elementary volume. Now it's difficult to identify and define what it is, but we sort of try, we did a lot of thorough comparisons with Anna Trakowska on how large the REV should be, how should you be looking at the influence of the boundary conditions and sort of what happens near the boundary or not. I encourage you to perhaps look at these papers with Anna that that I mentioned. All of them are, by the way, available from my website. So upscaling today, it's everybody knows how to do that. More or less, is you would start with a Stokes flow model in just the fluid domain. So here in those black regions, and you would upscale this to the Darcy model. So just a normal elliptic equation at the core scale. We can also work, and that's what we worked with Anna on, going from Navier-Stokes to non-Darcy, and there the interesting thing was the discovery what appropriate non-Darcy model we should have. Now, I'm not going to talk about transport today because this is a big, interesting, very interesting topic that I just don't have time to even touch on. What I want to talk is about the energy equation, which would involve a parabolic PDE. You would be upscaling heat conduction. So the coefficient that you have here are C and K, and both of them are dependent on the temperature because the they both depend on what phase you're in. So you would pose some kind of a heterogeneous heat equation at the pore scale, recognizing that the rock and liquid have different properties. And in fact, when there's a phase change, you would also have that rock, ice, and water have different physical properties. And so you will be solving this in the entire REV. There's work that informed us. Thank you very much for this work. Inga Berry and collaborators and Florian Radu, they have worked on geothermal energy applications, and they've completed some work on that. Now, what we did not find in literature before was the work on flow and energy with phase change when you go from pore to core. And this is really what we started working on about 2-3 years ago. So the heat equation now changes. Now you have, instead of just the conductivity here, you have a nonlinear, we say multi-valued graph, but the multi-valued feature here is really hiding a variable that you would really need to account for. So that additional variable is the amount of the fraction of water present. And there's, of course, latent heat involved, proportionally accounted for with that water fraction. So there are now, again, new interesting challenges. And this is what started really us, also from some earlier work on biofilm and methane hydrate. So in a nutshell, many of you already are familiar with the process, but I will state it anyway. I'm looking at the pore scale, where you would be solving for the flow only in those areas away from the gray, which are the grains, and you would be solving. So this is actually Navier-Stokes station or Navier-Stokes equation, and then you would be upscaling this one to Darcy or non-Darcy if you do have this inertia term in your equation. The big difference, of course, is, and everybody knows that difference, but it does surprise some people who are new to the subject that, of course, for the Stokes or Navier-Stokes model, you would be imposing boundary conditions on all of the U, whereas when you look at the Darcy or non-Darcy, you would be only imposing the conditions on the normal fluxes, if at all. And so the difficulty here is that for the intermediate models, such as Brinkman model, you have this transition zone where the boundary conditions all of a sudden have to switch from being, you know, the Stokes typical and to the Darcy typical. So what did we do? Well, you've seen this picture perhaps before, and I apologize if you did, and if you but here's what it is. We started looking at synthetic geometries. We worried a lot about using voxel grids versus you know, body fitted grids. We looked for this global trend of pressure. So here you have a picture on the left hand side in the corner where you see the profiles of the pressure, and you want to look at the global trend, but you still should be accounting for what happens and maybe at larger Reynolds numbers, and this is actually for a larger Reynolds number. Then we tested a lot of the grids. We upscaled this to the non-Darcy flow, so the K was fixed for a large number of the large range of the flow rates, but then you would have decrease for high due to the inertia. And then we looked at synthetic media, we looked at the glass beads, we looked at lots of fantastic data sets given by collaborators. And then most recently, we looked also at the biofilm data from Dorothy Wildenschen's group. We looked at propant, we looked at then the pore network approaches, which we were hoping would, you know, help us battle that tyranny of complexity. And to a certain extent, I can say we were successful, but there were still some questions open. So the main takeaway from this is that a lot of this mathematical theory that we use to prove theorems about whether the numerical methods are convergent or not, you have to abandon this when you're working in the pore space. And I listed a bunch of them here. And so this is just a cautionary tale. Occasionally, we just have to take off our mathematician's hat and maybe work with a practical, I don't know, geophysicist, the geologist helmet in order to be safe while we are doing those pore-scale simulations. All right, so now the question is, do we know everything? Are we all set to work with from pore to core, or maybe are we set to go from core to field? And you know, the big idea is, right, that you would replace the laboratory experiments or maybe the field data, that you wouldn't have to work with this anymore, and that you would just instead try this fantastic computational model that will just do it all, and then so you can just rest and while the computer is working. Well, the truth is, there is still a lot there to work with. And I will mention some challenges there. In particular, the computational complexity is really difficult. There is a lot of parameters that you would have to fit, and perhaps that's not really the way to go. What about the physics that might be different? And then what about all that nonlinearity? So we worked on applications where these challenges were also very important. In particular, the main one for these two applications, biofilm and methane hydrate, the difficulty is that you can't just work with images because there are not that many easy images that you could rely on. In particular, both biofilm and hydrate are very hard to image. Primarily because, let's say, biofilm would die if you subject it to X-rays, and then the hydrate would actually dissociate in a laboratory unless you maintain highly pressurized and very low temperature conditions. So there are lots of difficulties. Then, in addition to that, the pore-scale models that you would build are very expensive because the models involving free boundaries are very difficult. Also, the solutions you come up with very strongly depend on the, well, sometimes strongly, sometimes not so strongly, depend on the initial conditions, which are generally unknown and which might be totally random. So yeah, so upscaling all of that is difficult. So we looked at this, and we evolved, so to speak, from over the years, from thinking we can do it all, going to more and more complex geometries, more and more complex models, and now most recently looking at flow and energy equations. And we came up with some ideas that did not involve let's say, two-scale approaches, but rather involved reduced, or if you like, surrogate models. So we started building probability distributions. Here is an example of one from data. Then we started using these reduced models and come up with sort of lookup tables for the dependence on permeability on the volume of the obstructions when you have some new stuff growing in the porous medium, and I'll mention this in a minute. So in particular, we found that using DNS, so direct numerical simulations, was just overwhelmingly complex, also in view of the fairly large uncertainty of the initial conditions. You see here pictures, all of that appeared in a paper with Joe Umhofer and Choa Shin, where you see that we tried to use something other than the DNS. So we came up with a modified phase field model, which we call constrained localized phase field model, that gave us results similar to the DNS. We also worked with a wonderful lattice-based model, which reduced complexity by a factor of, I don't know, 10 to the second or 10 to the third. So think about what a big change that was. Fairly heuristic components of that model require that you have a really good Hamiltonian. But anyway, we're very pleased with the results. At the end of the day, depending on what kind of geometry you're working with and what kind of assumptions you're making, we got those kinds of reduced models for biofilm, where the new obstructions are coating the surface of the pores, or when you have them as pore filling. So for example, ice growing in porous media or hydrate crystals growing in porous media try to stick away from the grains. All right, so there we go, and we are beginning to see the physics that needs to be there. The takeaway is reduced or surrogate models and using uncertainty to your advantage rather than worrying about whether it really is meaningful to do all of this. So physics now, that's what came up when we were working on those different biofilm models in particular. It might not be obvious to everyone, but scale matters. And in particular, here I'm just giving as a simple example what happens when you're using a Brinkmann model to simulate flow at the pore scale. And this is just a zoomed in example. Solving a problem with exactly the same physical values of the coefficients, which you get from the literature, in particular for that resistance term, in the sort of the Darcy component of the Brinkmann model, but changing the length scale from 10 to the -2 of the millimeter versus all the way to a millimeter scale, you see how strongly the results depend on the length scale. So of course that might be obvious to everyone, but it wasn't certainly obvious to us. And in particular, what this means is that you might not really need to have some of those models that you develop depending on the length scale. So that was perhaps an eye-opening experience for us. Secondly, the two other very important physics at the pore scale that we looked at involved generally thermodynamics, and in particular the phenomena of wettability that connect also to capillarity. And I'm pointing out here to fantastic work that I became aware of by Ryan Armstrong and collaborators, as well as in computational modeling by Beatrice Rivera and Florian Frank and others that simulated these things at the pore scale. So just to point out to you, the physics in the micropores is really completely different than the physics at the Darcy scale. So this affects a lot. So moving forward now to our recent project, we are working on coupled TH and perhaps eventually in THM, so including mechanics coupled to thermal and hydrological processes in permafrost. So we look at upscaling from the pore-scale, the heterogeneous Stefan model, to the Darcy scale. And the two difficulties are, well, if you just directly upscale the Stefan problem, so you're going to get something then that looks like this picture on the right-hand side, where you are basically reproducing for, let's say, 3 materials, you would be reproducing piecewise sort of multi-valued graph when upscaled to the Darcy scale. Well, that's not really what engineers see. Engineers measure things that look more like this graph on the left-hand side. So I caution you here, you need to know the physics and need to introduce the physics. So here's what we did. We did that also simultaneously. We were running a lot of experiments, in particular Lisa Bigler's PhD included a lot of simulations at the pore-scale, which were upscaled. And in particular, what we saw was that the liquid fraction behaved just like the one you would see at the Darcy scale. So with this, we were able to match the physics, provided we include additional physics, and that physics was the perhaps well known to a lot of different people, the fact that there's a freezing point depression in small pores, otherwise known also as the Gibbs-Thompson effect. And so with this, we were able to get pretty good matches. I just showed you a minute ago on this other slide. And with these approaches, we're also pretty much able to compute the effective heat conductivity. And I'm not going to talk about the permeability at this point today, which we were able to match to what people see in the literature, geotechnical literature for permafrost. So this was very gratifying. Now, the takeaway from this is, and from this picture, if you have a chance to study it in detail, is that the geometric average approaches that the geotechnical engineers use, so plotted here in red, sort of sit in between, which we always know happens, but are not bad proxies for the heat conductivities that are upscaled from pore-scale. But I do want to mention that they can be quite different. So if you see here the difference between the anisotropic values, clearly, since we are thawing this ice region from bottom to top, you should be perhaps looking at some other than just those geometric averages. But more work is to be done. And at this point, I will start wrapping up. So the reason why I gave this talk a title involving seriously, the keyword seriously, is because I believe that there's still a lot to be done, a lot to be learned. We need to use multiple scales, but we should not be throwing away the physics. Again, if we're only looking at the mathematical models that are given to us without looking at more complicated models, and if we are not informed by the physics, then we might not be solving the real things. The things that we do from pore to Darcy inform very well what we do from core to field. So in particular, my pet project here, going from pore to Darcy to landscape, we know that we're going to have to look at a lot of non-equilibria. And so there goes my last slide after this, in which I will show you some data that we were able to look at. The data that show, this is a picture from Lisa Bigler's thesis, that in the simulation, we distinctly see hysteresis. When you are warming, you get a different dependence of the enthalpy on the temperature than if you're cooling. And this is the same what you would see when you're processing data. I have some data that we processed, and thanks, Noreen, for getting the data to me. You see distinctly that the measurements, there's some difference, non-equilibrium, which is reflected by the hysteresis. So there's more. We're going to work on this more and enjoy it. And I hope you will all enjoy it as well. And I want to thank again to the SIAM Geosciences officers for this wonderful webinar, and for the community for keeping it going. And again, I apologize if I omitted some of the citations to your work, but so is life. I can't always do it. Thank you very much for listening. Thank you.
Thank you, Malgo. Wonderful talk. I have to just quip that if there is a porous medium, there will be hysteresis. There's no way around it. Anyway, so Sorin, I have unmuted you. We have a question. Would you like to pose your question live, or I can read it? Either way works.
Thank you very much. I'm not sure if it works.
It works. We can hear you.
That's a miracle, because yeah, okay. Thank you very much, Malgo. That was a beautiful talk, and thanks for thanks again also to the organizers for this wonderful sequence of presentations. Malgo, you mentioned Stefan problem, which is of course a very interesting one and tough. I mean, you mentioned homogenization of it. If I understand correctly, you were discussing about homogenizing this as a microscale model. Yes.
Oh yeah, and yeah. So I just read your question in the chat, so I can answer it really quickly. Yeah. There is a paper by Augusto Vicentin from 2007, which I hope I put somewhere on my slide. Let me see if I did. If not, otherwise I'll just send you the link. That provides a rigorous explanation why upscaling let's say the usual multi-scale graph works. And the way this is done is you go to its primitive, so the convex functional, you upscale the functional, and then you take the subgradient. So from that you get the rigorous result. Sorry, I'll share with you the reference, if you will. It's very in SIAM Journal Mathematical Analysis. So and it works for doubly nonlinear Stefan type problems. So you know, there's rigor behind what we did, but we actually this calculation here on the slide right here was following exactly what Vicentin's rigorous work suggests, except that we applied it to the case, in this case, with 3 materials. So we have a paper that's has been close to being completed. So I'll share this with you as well when we're done.
I mean, this was not completely, sorry, I mean, but also this one means the model is written in the full domain. You don't see the free boundaries directly. I would say you don't work in time evolving domains. Let me put it like this. Or do I see it wrongly?
No. We are working with the free boundaries at the pore-scale. As an example here, that's what we see. This is how you would be, yeah. So the most accurate way would be to actually have a micro model, right? To have a 2-scale connection between them, so that you can, you know, find at every point of time you can find the right K. But pre-computing the nonlinearity under the time derivative is completely possible without this. But as I said, also, unfortunately, doing it this way. Okay, so doing just the rigorous way without including additional Gibbs-Sump effect, you don't actually get the correct physics.
Right.
So what we have to do is we have to include so-called undercooled water and to look at the freezing temperature of the different pores. So here you have an example how looking at the random distribution of pores, you would come up with, you know, you can get the right qualitative behavior. I guess that's what I'm saying. You see here the magenta curve, so you can get the upscaled and which will come pretty close to what the engineers use as the permafrost scale. So I'll be happy to talk to you some more on this. I know you're an expert on Stefan problem and as well as on homogenization. So I think we have a lot of good talks maybe coming up. So
will be great. Thank you very much.
In Bergen, if not sooner. Bert.
Yeah.
Bert, did you have a question? I allowed you to talk, or is it just a comment?
No, it's just a comment. That's all.
All right.
Good talk,
Well,
Malgo. It was great.
Thank you. So Bert, thank you for that comment. I find that the physics is, of course, quite challenging when you're trying to learn everything from, let's say, as a mathematician, computational mathematician, right? You're trying to do it all. And physics frequently is not quite there, at least not that kind of a scale physics. Physics of wettability, physics of, thermodynamics of in confined regions is not part of the standard curriculum that people, let's say mathematicians usually get. So myself included. So
No, it's interesting
that's
because
challenging.
there's a really neat problem in drying paper products, essentially, when they make paper. So there's a phenomenon that's called capillary condensation. So effectively, you can get water that will kind of form in very small pockets, even though the temperature is superheated. And so in a lot of this fabrication, they want to remove this water that's actually there, and that's why it's actually very expensive to remove it. So it'd be similar. It'd be a similar idea as this, I think.
Yeah. So this, by the way, we came across capillary condensation when we were working on adsorption phenomena, again, which we looked at also using those MCMC approaches. So sort of reduced models with a particular Hamiltonian, but yeah, it's very closely, and there's hysteresis there, of course.
Yeah, of course it does.
Yeah.
I was about to say,
which is also partly how we came across those models. So yeah, Masha, I agree. Hysteresis is everywhere. The big question, though, there is how significant is it? Right. So when we worked on non-equilibrium capillary pressure and hysteresis, and Soren knows all about that too. That's very significant. But then when we looked at relative permeability and hysteresis in relative permeability, at some point I became convinced after some conversation, I think at some SIAM GS meeting, that it's not all that significant. But now I'm actually thinking it's perhaps perhaps it is significant.
I think it depends on the thermal field around it, right? So if you're thinking in geological scales, the temperature gradients usually aren't that steep, so it may not be as relevant. But for these drying problems, they're looking at temperature jumps on the order of 1 to 200 Celsius. They're trying to really crank up the heat very quickly.
Well, so the question that I will stick this comment here is, when you say that they are looking at temperature jumps, my question is, not being an experimentalist, but is like, when you measure the temperature, you measure the temperature where?
Oh, this is outside. This is outside the paper.
No. I understand. But in all of the results that we're looking at, you're always measuring the temperature at a point. So it's clear that temperature measured at a point is not necessarily in equilibrium with anything else at some other scale, right? So that's the general difficulty, right? That equilibria are kind of a hard thing to look at, and you have to play the game between, is it significant that you have non-equilibrium? I believe it's very significant when you cross a lot of length scales. Just like between, I don't know, pore-scale and Darcy scale, or between Darcy and field scale, as we have seen in this data from Alaska. So,
right. I guess I'm thinking more in terms, the engineers are going to say it's significant if it affects whatever they're designing. Right. So you're right, though. Essentially, you can have very small effects add up over sufficiently long scales. Right?
Actually, I heard that comment that it's insignificant by the engineers that didn't, I guess, really want to deal with it, and so they said it was not significant. So it was the opposite. But nothing to say wrong about engineers. If we love you, and I'm probably a closeted engineer myself. So
okay, thanks, Olga.
Thank you.
Well, one comment is that one could probably, if one needs a brief geometric test whether something is significant or not. Volume fraction is only maybe that test, but one could quickly see the spatial distribution if one exists through computational approaches. And to me, that's the key benefit of having computation, is like, does your phase that you're looking in, say there's sorption and you have capillary condensation, well, at some point that those capillary condensation, they could connect. And as they do, they become significant. If they're just isolated and scattered, they're not, right? So there's a spatial component that is captured in a lot of computation or imaging that is relevant in deciding.
So
But
so
once you homogenize, I don't know how you get to that.
So I do have a question for Masha then, since you're so close to the, all the imaging and what are the new techniques that might be able to reveal, the fine features of what's happening at the pore-scale when you have materials like, ice and water, other than, I don't know, using some kind of tracers, or just like Darcy did for the biofilm with the barium that doesn't penetrate the biofilm, and so on, so on. Are there new techniques that can distinguish between, because the ice and water really have similar densities, so they would have similar attenuation coefficients and stuff. So what are the new, what is the future?
SIAM and cryo SIAM. But the problem with those is that you're going to get technically a two-dimensional view, and then reconstruct something in 3D is a little bit problematic. But combination of basically microscopy techniques, because
is this destructive?
You can also fire different things at your material, so you can actually get elemental composition that can be useful and overlain. It is data intensive though.
What about, it's destructive, right?
It is, can we actually process it?
It is destructive though, right? Isn't it? It's, yeah, that's my concern, that we could not probably use it for any kind of like in time simulations, because you're looking at a different.
Depends, because if you're actually looking at in time, the best ability to resolve time would be actually direct microscopy. I don't know, freezing would be of course challenging, right? But or a high temperature change, because you got to have a microscope in the picture that you got to work with. But basically you can monitor everything under a microscope, so there's a lot of reactive flow that is observed that way. In my department, Ben Song does that, and also there's a number of people at Stanford and so forth, and that way you can get the time scale that you cannot right now get with microtomography. You can if you have like a really cool toy like the Switzerland the fast tomography. So fast tomography is getting there too. It's just three-dimensional data that come out are huge. All right. Are there any further questions? We are losing the audience. We're like chit-chatting here away, but I guess we did manage to finish the main portion of the talk on time, and the rest of this discussion will be recorded. And Matt Evans says thanks for the talk. All right. Yeah. Well, thanks, thank you, everybody. Thanks to all of you that have joined us today. And we are going to post the recording of this. So we're creating a library of knowledge.
Oh boy. Thank you. Thank you very much, Masha. And again, thanks to Chris and Masha for standing in here as the officers. Thank you.